Okay, thank you. All right, so I said that there was this case of a degree 4, some cases of degree 4 CM fields were proved by Tong-Hai Yang by doing some sort of arithmetic intersection calculations on a Hilbert modular surface. A Hilbert modular surface is a special case of an orthogonal Shimura variety. And the proof of this averaged version of Kolmez is all about doing arithmetic intersection calculations on some integral model of an orthogonal Shimura variety. So I now present to you an orthogonal Shimura variety. Okay, so step 1 is to construct some quadratic space over Q. And I'm going to construct the quadratic space over Q in such a way that it knows about our fixed CM field E. So fix a CM field, first of all. E. Okay. And label all of its complex embeddings. So there's going to be a sigma 1 and then its complex conjugate all the way down to sigma D and its complex conjugate. Those are going to be all the embeddings of E into C. And I'm going to choose, it's an arbitrary choice, choose some element Xi in F cross that's negative at the first embedding, but positive at all of the others. And from that choice, I can construct a quadratic space. So it's going to be some Q vector space with a quadratic form. The underlying Q vector space is just the field E itself. And the quadratic form is, well, if I give you an element of E, I can multiply it by its complex conjugate. That'll give me an element of F. Then I multiply it by this chosen element Xi. And then I just take the Galois theoretic trace from F down to Q. I mean, it's maybe the details are not so important. It's just I've constructed some quadratic space that in some way knows about the E that I started with. And now assume, for simplicity, that there exists some lattice that's self-dual. In the sense that the bilinear form bracket xy defined by q of x. I mean, I've given you a quadratic form. There's an associated bilinear form. There it is, and assume that this bilinear pairing identifies the lattice with its dual. I was thinking about this preparing the talk. I actually think that no such lattice ever exists, given the way I've constructed the quadratic space. I mean, what you really have to do is, inside of this quadratic space, choose a lattice that's as close as you can get to self-dual, meaning minimal discriminant. And everything I'm going to say under this bogus assumption that it's self-dual, you then have to replicate in this as close to self-dual as you can get. But I mean, that would be too awful to present in a talk. And so I'm just going to make this assumption, and it makes everything much easier. From this quadratic space, I can construct a complex manifold, a Hermitian domain. That I'm going to call D. D is going to be, it's going to live inside of projective space over the complexification of V. So it's going to be some set of vectors. It's going to be, all of the vectors are assumed to be isotropic. Okay? So I can look at the quadric hypersurface of isotropic lines in projective space, and then I want to impose an open condition on that, which is that z bar is negative. So this is some complex manifold of dimension 2D minus 2, 2D minus 2. I'm always assuming, by the way, that D is not 1. Because the case where D is 1, we're just looking at quadratic imaginary fields, and it's just the Challis-Selberg formula, and it's done. So we only have to deal with D greater than 1. And, okay, here's my orthogonal Shimura variety. M of C, it's just you take this Hermitian domain, and the special orthogonal group of V acts on projective space, and it preserves all of these conditions. And so I can mod out by SO of the lattice, some discrete subgroup. And that is, well, it's a Shimura variety. And I want to convince you that it's wonderful. So, I mean, you should all be looking at these. So this has all kinds of extra structure. Okay? So here's some of the extra structure on it. First of all, I'm going to explain why it comes with a distinguished point. Woohoo! It comes with a distinguished line bundle on it. It comes with a distinguished family of divisors on it. And the least obvious one of all, it comes with a distinguished family of abelian varieties that lives over it. And all of these things interact in some interesting way. So first of all, there's a distinguished point. That I'm going to call Y. Okay, what is this distinguished point? Well, the distinguished point actually lives back here in the Hermitian domain. I claim that in the complexification of V, there's actually a distinguished line. And there is a distinguished line because of the way that V was constructed. So if I complexify V, that's just E tensored over Q with C. But E tensored over Q with C is just a bunch of copies of C. And I've labeled them in some way. So I send alpha tensor 1 to sigma 1 of alpha, sigma 1 bar of alpha, and so on. And back when I chose this element C, I sort of broke the symmetry between them and singled out the first one. And that condition on C implies that, in fact, this first factor sitting inside of VC as a line actually lies in this Hermitian domain. It's isotropic, and it satisfies this condition. So, this line is some C, Y in D. And then you just take its image in the quotient. So that's my distinguished line, which gives me a distinguished point. Okay, let me do this. Yeah, it's better. Okay. Okay, I said there's a distinguished line bundle. That's obvious. So the tautological line bundle on D is just the pullback of the tautological line bundle from projective space. So it's going to be called omega. Has fiber omega Z. I mean, its fiber at Z is the line that Z is. Okay, that's not interesting. Well, it is interesting, but more interesting is the fact that this line bundle carries a canonical metric on it. So to put a metric on the fiber at Z, I just have to tell you what I want the absolute value of the vector Z to be. Well, I take the pairing of Z with Z bar, and then take minus that. So we have a metrized tautological bundle. Okay. So this line bundle with this metric, I'm going to call it omega hat, and it lives in this space pic hat of metrized line bundles on what at the moment is just a complex manifold. Okay, other structure. There's a family of divisors on this. So fix some positive integer. If x is some vector in V with q of x equal to m, then I can define an analytic divisor dx on D. And it's just, I mean, D is a collection of lines in V. You just take all of those lines that are perpendicular to this fixed thing. The set of all z in D such that the line CZ is perpendicular to x. You can check that's codimension 1. And now I just assemble all of those x's that lie in my lattice that have norm m, put all of those divisors together, and then take the quotient by the action of SOL. So Zm of C is going to be, you take the union over all x in our self-dual lattice, q of x equal to m of this divisor dx, and then the group SOL acts on that whole thing, and then that's sitting inside of m of C. So maybe I should say, if D were 2, then this M would be a surface, and it would actually be either a Hilbert modular surface or some weird twisted quaternionic version of a Hilbert modular surface. And these things would exactly be what are called the Herzebruch-Zagier divisors on the Hilbert modular surface. What board am I at? I'm not there. I'm over here. Okay, and then there's one last extra structure. I said that there was some family of abelian varieties that lives over M. And so this is the part that's really neat. So if there are any fans of K3 surfaces in the audience, this might ring a bell. So there's a Kuga-Satake family. Of abelian varieties. That I'm going to call A. At the moment, everything is still complex, so I'll keep writing M of C. It's huge. I mean, every fiber, so the relative dimension is 2 to the 2D minus 1. So it's a big abelian variety. How is it constructed? Okay, it's through the magic of Clifford algebras. So there's a Clifford algebra. Associated to the quadratic space. By definition, it's just you take the full tensor algebra of V, the direct sum of all of its tensor powers, and then you mod out by the two-sided ideal generated by Q of x minus x tensor x for all x in V. So you just take the full tensor algebra and you declare that every element squared is equal to just its quadratic norm. And V sits inside of the Clifford algebra, just sitting in the degree 1 tensors. And using this inclusion, you can do the following funny trick. So every z in D is, remember, a line in the complexification of V. So I can view z as a line in the Clifford algebra. And then inside the Clifford algebra, I can just multiply by that line. And so what you get is some subspace in middle dimension. So every D gives a subspace Z times the complexification of the Clifford algebra inside the complexification of the Clifford algebra in middle dimension. So really what I'm constructing is a variation of Hodge structure on D. This family of middle dimensional subspaces here. And then you can let C of L inside of C of V be the subring generated by the lattice L. And then we get, attached to this point Z, we get some abelian variety. Complex torus at the moment, AZ, which is just you take the complexification of the Clifford algebra modulo the left ideal generated, right ideal generated by Z modulo this lattice inside of it. It looks mysterious, but that's a complex torus. And so this gives an analytic family of complex tori living over this domain D. And you can check that, these are polarized variations of Hodge structure, polarizable variations of Hodge structure. So it's actually a family of abelian varieties, and it actually descends to the quotient M. So that gives you this. Okay, so I'm going to do this first. What can we say about this? Well, there's a lot you can say just from the general theory of Shimura varieties. So theorem of Shimura, Deline, and I need to throw in Michael Harris as well. What am I doing? My coffee wore off. Oh, that's tea. No. Any port in a storm. Okay, 1. Well, I would agree the theorem is really that all of this stuff is defined over Q. So there exists a smooth variety M over Q whose complex points are the ones that I just constructed. M of C equals M of C. And everything is defined over Q. So this family of complex abelian varieties is actually defined over Q. Omega is algebraic. The line bundle, the tautological bundle is algebraic and defined over Q. That's why Michael Harris's name is here. It's part of the theory of automorphic vector bundles. These analytic divisors are all actually algebraic and defined over Q. Same for the Z of M. And what am I forgetting? Oh, and well, M had a distinguished complex point that I called Y. And that's not defined over Q, but it's defined over the CM field E that we started with. Okay, and then there's a further theorem. The further theorem is due mostly to Mark Kissen, with some bells and whistles, due to Matapusi-Para, together with Wanzu Kim, and part due to Andriata, Gorin, Yi, Matapusi-Para. So the first part is the hardest part. So this smooth variety over Q extends in some canonical way to a smooth scheme over spec Z. So there exists a smooth extension So now we get to the integral models. I have my m over spec q. And this thing can be smeared out. Everything integral is going to be with curly letters. So this is smooth. I mean, let me just say, so the construction of script m is really easy. It's the proof of smoothness that's hard. The construction is, well, we've got a family of abelian varieties over m. You can endow it with a polarization in some natural way. And then just tautologically, this family of abelian varieties over m defines a map from m into the moduli space of abelian varieties of some dimension. That moduli space then has an integral model. And so now that you've embedded m into something that has an integral model, you can just take its Zariski closure. And that's the definition of script m. But then it's clear from the construction, I mean, this thing now by definition comes with a map to the moduli space of abelian varieties. And so you can just, on that moduli space of abelian varieties, pull back the universal thing. And this abelian variety over m extends to an abelian variety over the integral model. Okay, so that extends. 3, well, omega has a natural extension. To m as well. That, I think, is like it's implicit in what Mark proved, but it's explicit in the paper of Metafusi and Perrin and Kim. They show that this integral model has a theory of automorphic vector bundles on it, in the sense that if I give you any algebraic representation of the group SOL on some finite rank Z module, that representation will determine a vector bundle on M, and that vector bundle has a filtration on it. And in our case, I mean, SOL has a canonical representation. It acts on L, which means there's some canonical vector bundle on M with a filtration, and this omega is just one step of that filtration. It's the lowest non-zero step. So we get, again, some metrized line bundle now on the integral model. These names are here because we constructed an extension of these divisors. Script Z of m, two divisors on script m. The definition is not by taking the Zariski closure of the thing you have in the generic fiber. It's some sort of moduli theoretic definition. This is the locus of points in M at which this abelian variety acquires an endomorphism with some complicated list of properties, and among those properties is that its square is multiplication by M. And then one can prove that most of the time, that actually just gives you the Zariski closure of the generic fiber. But there are some weird low-dimensional cases where that fails. But anyway. And finally, this special point that's defined over E. So Y, I'm going to think of as a map from spec E to M, and it extends to some script Y from spec OE to the integral model. Proving that amounts to proving that if you take this abelian variety and take its fiber at this point, you have to prove that it has everywhere good reduction. But you prove that by proving that at this point it actually has complex multiplication, and anything with complex multiplication has potentially good reduction everywhere. But we'll come back to that point soon. But now, if you look at what I wrote, you should notice there's something interesting here. Because in this M, what do we have? We have a family of divisors in codimension 1, and spec OE is a one-dimensional scheme. So we've got this fixed one-dimensional thing floating around, this whole family of codimension 1 things floating around. A natural thing to do is to start intersecting them and see if that gives anything interesting. And it will. Okay. I stop at 4:30. Okay. Good. Okay, so on that note, let's talk about intersecting things. Yeah.
It doesn't matter, but are you saying that the particular class of diagonal varieties we're looking at has enough level structure but not have?
No. What I'm saying is that I'm sweeping all stacky things under the rug. And this M is, in fact, a Deligne-Mumford stack. And this extension, you have to pass to some finite extension of E. And I mean, everything in sight is a stack. And I don't want to talk about it any more than that. Yeah. Okay. Arithmetic intersection. Okay, so here's a definition. An arithmetic divisor on this integral model is, they're going to be called z hat, and it's a pair, z, g, where z is some honest Cartier divisor. Well, yeah, honest Cartier divisor. And g is a green function for it. By which I mean g is a smooth, well, it's a smooth real-valued function, except where it isn't. So I'm not assuming anything about harmonicity or anything. I really want to allow any smooth function. Smooth real-valued function on M of C, except where it's not defined, where it has a logarithmic singularity, which is along this divisor. Now, I mean, the simplest example of such a thing e.g., any rational function f on M determines an arithmetic divisor called div hat of f. The underlying divisor is just the divisor of f in the usual sense. And the Green's function, I'm going to take minus the log of the absolute value of f. So these are called principal arithmetic divisors. And I mean, in exactly the same way that the Picard group of line bundles is the same as divisors, mod principal divisors. By sending a line bundle to the divisor of any rational section, the group of metrized line bundles is isomorphic to arithmetic divisors modulo the principal ones, just by sending a metrized line bundle L to, again, you just choose any rational section, and you send it to div hat of f, which is the same. I mean, instead of a rational function, I now have a rational section, but div hat of f still makes sense. I just take the divisor of my section in the usual sense, and instead of the absolute value, I just use the metric on my line bundle to take minus log of the norm of f. Yikes. Okay. Good. Now, suppose I give you an arithmetic divisor. So I can form its arithmetic intersection against this fixed cycle of dimension 1 over here. Can form arithmetic intersection. So I'm going to call it square bracket. Against this fixed one-dimensional thing that we've got. And so how is that defined? So it's a sum of two terms. I mean, it's essentially the usual scheme-theoretic intersection. I mean, z is in codimension 1, y is in dimension 1. I can intersect them, and hopefully the thing is in dimension 0. Scheme-theoretic intersection multiplicity that I'm just going to call z of m dot y. It just, I mean, in practice, all of these divisors actually intersect this fixed thing in dimension 1 properly. The intersections are all zero-dimensional. And so this scheme-theoretic intersection basically just means that you intersect these, the scheme-theoretic intersection, it's going to have no rational points. It's supported in finitely many non-zero characteristics. You take the scheme-theoretic intersection, you count the number of points in it, but you weight each point with the multiplicity of the local ring of the intersection, which just means you count it according to sort of the tangenticity of the intersection, if that's a word, which it almost certainly isn't. So there's a finite part that just doesn't know about the Green's function, only knows about the divisor. But then you subtract off the sum over. So at some point I said that you could prove this averaged Kolmez conjecture by enlarging the field, CM field E. So I'm just going to assume that it's Galois. And then I can sum over all sigma in the Galois group of the log of the absolute value of the Green's function evaluated at sigma of y. So I take our distinguished point that's defined over E, I look at all of its Galois conjugates, I evaluate the Green's function at all of them, and I throw that in. So a finite part and an Archimedean part. And then it's an exercise to check that if your z hat is actually a principal arithmetic divisor, then this intersection is always 0. So this intersection pairing descends to the quotient. So this defines a linear functional called arithmetic intersection against y from pic hat m into the real numbers. There's another way to define this, which gives the same definition, which is that any metrized line bundle on M, I can pull back to a metrized line bundle on Y. And if you're a normal person, you look at spec OE, and you think, well, that's the set of prime ideals in OE. But if you're Arakelov, you look at the set of prime ideals in OE, and you think, that looks an awful lot like a compact Riemann surface to me. And so a line bundle on it should have a degree. And so Arakelov defined the notion of the arithmetic degree of a metrized line bundle on spec OE. And another way of defining this is just take your metrized line bundle on M, pull it back to Y, and take its Arakelov degree. And now, I erased it, but this tautological bundle that's algebraic and defined over Q extended to the integral model, and it has a metric on it. So we have a distinguished element here, omega hat. And we can plug that into here. And here's the theorem. You can compute that degree in two different ways. And if you compute it one way, you get the sum of all the Faltings heights as you vary over the CM types. And if you compute it a different way, you'll get the sum of all the Kolmez heights. Okay. Now, one of these is relatively easy, and that's the connection with the Faltings height. So that comes for the following reason. So it is almost true. I mean, I've never really, we've got this family of abelian varieties, we've got this line bundle, we've got this point, we've got these divisors. I haven't really explained to you the ways in which they're all connected, but this line bundle is very closely connected to this family of abelian varieties. It's almost giving you take this family, you take its Lie algebra to get some vector bundle, and then take its determinant, and that's almost what omega is. In fact, that's literally true if you take each one of those to some appropriate power. But let's ignore that and just suppose that omega actually is the determinant of the Lie algebra of this integral Kuga-Satake thing. Well then, at any point, z in M, what does that mean? It means you can identify the fiber of this line bundle with the global top degree algebraic differential forms. And under this isomorphism, which exists if you take appropriate powers of everything, here we have a metric, and that metric comes out to essentially be integration of a top degree holomorphic form against its complex conjugate. In other words, this line bundle was just born to compute Faltings heights. So using this, it's pretty easy to see that if I compute this arithmetic intersection against y, what it's giving me is I take this Kuga-Satake thing, I restrict it to spec OE, to y, and then I take its Faltings height. So A restricted to y. Because I've already said that this A has complex multiplication. To zeroth order, you could now imagine that when I take this A and restrict it to my distinguished point, it breaks apart as a product of things, each of which has complex multiplication by OE, and all of the different CM types occur with multiplicity 1. And then it would be clear that you'd get this. That's actually not what happens. It's a little bit stranger. This thing does break apart into a product of abelian varieties, each of which has complex multiplication, but it's not, the complex multiplications aren't by the CM field E again. Every CM type of E has a reflex CM field, and when you break this apart, what you actually get is complex multiplication by all of the different reflex fields that can occur as all of the CM types vary, and then you have to make some argument to show that that is actually the same as this Faltings height. But it is. So that's the easier one. Let's see, so I have 11 minutes? Yes. Good, okay. That means right here, there's a page labeled panic, which is what I do if I have 2 minutes left. But we don't have to panic yet. Okay. Where am I? Okay, now, we have to compute this in some way where somehow an art and L function is going to appear. Well, it would be nice if we could have some rational section of that line bundle omega whose divisor we could compute in some explicit way. I mean, actually, compute this intersection pairing. And so these sections, there's a systematic way to construct rational sections of powers of omega. And this is the theory of Borchert's products. So let, well, let's see, how much of this do I really want to say? So let f of tau equal the sum over m. Okay, so f is going to be a weakly modular form of some weight, where weakly just means we're at full level SL2z, but I'm allowing poles at the cusp. So sum over m much greater than minus infinity of c of m q to the m, b weakly modular of weight 2 minus d. So here's a theorem that's mostly due to Borchert's. And then there's some improvements due to Fritz Hermann and myself with Kirti Matapusi-Para. Given such an f, there exists a rational section psi of f, called the Borchert's product, or Borchert's lift of f, of a particular power of this line bundle. The particular power is the constant term in the Q expansion, such that its divisor is a linear combination of all of these special divisors z of m, and the coefficients are exactly the negative coefficients appearing in the Q expansion, the polar part. So c of minus m, and the sum is over m greater than 0. Okay. Why is there a bunch of names here? So Borchert's proved this, but everything that Borchert's did was just on the complex fiber. And so you have to do something, first of all, to argue that this thing is algebraic and defined over Q, and then you have to compute its divisor on the integral model. And this was done by Fritz Hermann. So under that assumption that we had a self-dual lattice, and also under the assumption that this M that we're working with, this Shimura variety, is not compact. Because if it's not compact, you have a theory of Q expansions, which you can use to analyze what its divisor looks like. And then removing that self-duality hypothesis and also removing that non-compactness hypothesis is what Kirti and I did. But this means that in pick hat, it means precisely that this omega hat tensor C0 is represented by the arithmetic divisor div hat psi of f, which is this sum over m greater than 0 of c minus m z of m, and minus the log of the norm of the Borchert's product. So we can compute this, at least after multiplying by c of 0, if we can go and compute the scheme-theoretic intersection of y with every one of these z of m's, and compute the values of this Borchert's product at all of the Galois conjugates of this distinguished point y. And in fact, one can do this. I don't need to say that. Right. So the existence of this Borchert's product implies that C0 times the intersection of omega hat with y is now equal to, well, the intersection of div hat psi of f with y, which is now minus the sum over all the Galois conjugates of the log of the norm of the Borchert's product at sigma of y, plus the sum over m greater than 0, c minus m times the intersection multiplicity of z of m with y. Okay, now you have to compute two things. And luckily for us, that's the non-movable word, that's fine. This was already in the literature. So this methods for evaluating Borchert's products at CM points of orthogonal Shimura varieties. So let's call this term 1 and this term 2. Methods for 1. So the first appearance of such thing was in the Maryland PhD thesis of Jared Schofer. He was a student of Steve Kudla, and he was evaluating Borchert's products at CM points of modular curves in order to give a new proof of the little Gross-Zagier theorem, the one on prime factorizations of J invariants of elliptic curves with complex multiplication. And then he apparently, so Kudla told me that it was quite a traumatic experience for him. He thought he had finished everything and then found a gap, and it took him 4 months to fix the gap. And the 4 months of believing that all of his hard work was for nothing traumatized him, and he became a high school math teacher. But his thesis was really great. I mean, okay, that's not exactly, I mean, there are worse things to do, of course. But he decided he just didn't want to do research, and so he abandoned this. And then it was picked up by Brunier and Yang. And then further generalized by Brunier, Kudla, Yang. And since I'm running out of time, let me just say, they can compute this. And what they get is 1 equals lots of stuff. Lots of stuff really means it's essentially the Fourier coefficients of the derivative of a Hilbert modular Eisenstein series determined by the data E and F. And this lots of stuff is a bunch of Hilbert modular Eisenstein derivatives of Fourier coefficients, and somewhere in that lots of stuff is the constant term of the Eisenstein series, and constant terms of Eisenstein series are L functions. Lots of stuff, including exactly the thing that we want. This term coming from the constant term of the Eisenstein series. And then 2 is what most of the hard work in our paper is. And after long calculations, we can compute all of these things. And when you take this particular linear combination, you end up with minus the exact same stuff, but without this term. I mean, it's kind of a mysterious way to end the talk. Equals minus same stuff. But I mean, this is very much in the spirit of the Gross-Zagier theorem. And if you've ever looked at the proof of the Gross-Zagier theorem, the idea is there are lots of clever ideas that get you down to heinous computation, and then you just plow through them. So there are ideas that get you down to heinous calculation, and then you plow through them. And you end up with exactly this minus the same stuff, but no L function. And so you add them together, and you get the L function, which is precisely this. So that's it. So I'll stop there.